electrons are produced, and accelerated to bombard with target on anode side. X-rays are produced from target by characteristic and Bremsstrahlung processes. In this video, we will be discussing what happens inside an X-ray target, so that characteristic X-rays are produced. Let's get down to the atomic label of X-ray target, as X-rays are produced inside an atom. Here is an electron, which is thermionically produced from filament, and accelerated by potential difference between anode and cathode. This electron spends part of its kinetic energy to remove one of inner shell electrons of an atom inside target. This creates a vacancy in the inner shell. Atoms with a vacant inner shell are not stable. One of electrons from an outer shell will jump to fill the vacant inner shell. In order to jump from an outer shell to the vacant inner shell, electron must radiate energy, and energy is radiated in the form of electromagnetic radiation. Amount of energy released will be equal to difference of energy of outer shell and inner shell. If the energy of emitted electromagnetic radiation falls in the range of X-rays, we call it a characteristic X-ray.
For understanding of characteristic X-ray spectrum of tungsten atom, we need to first know its energy level diagram. A neutral tungsten atom has 74 electrons. K shell is the innermost shell and contains 2 electrons. L shell has 3 energy subshells, and contains 8 electrons. M shell has 5 energy subshells, with 18 electrons. N shell has 7 subshells, containing 32 electrons. 8 electrons are distributed in 3 subshells of O shell. 2 electrons are present in 1 subshell of P shell. Energy of electrons in K shell is minus 69.53 kilo-electron volts. That means minimum energy required to remove an electron from the K shell is 69.53 keV. If high-speed electron from cathode side has kinetic energy equal or more than 69.53 keV, then only it can knock out orbital electron from K shell. Once an electron from K shell has been removed, one electron from outer L, or M, or N, or O, or P shell will fill the vacancy in K shell.
Let's calculate energy of X-rays due to transition from L shell to K shell. Transition of electron from L1 subshell to K shell is forbidden. Spectral line or X-ray resulting from L3 subshell to K shell is called K alpha 1 line. Energy of K alpha 1 line equals binding energy of L3 subshell minus energy of K shell equals 59.32 kilo-electron volts. Spectral lines resulting due to transition from L2 subshell to K shell is called K alpha 2 line. Energy of K alpha 2 line equals energy of electron in L2 subshell minus binding energy of K shell equals 57.98 kilo-electron volts. K alpha 1 is the most intense characteristic X-ray. K alpha 1 is almost twice intense than K alpha 2. The relative intensity of the K X-rays are greater than that of L, M, and characteristic X-rays. Except for K X-rays, all of the characteristic X-rays have very low energies. L and M spectral lines of tungsten are of energies near to 12 keV and 2 keV respectively. If we draw spectrum with wavelength, the order of spectral lines will reverse, as energy and wavelength are inversely proportional. Characteristic X-rays are produced during inward electronic transition. If energy of emitted electromagnetic radiation is more than 100 electron volts, we call it an X-ray. If below 100 eV, it will be an ultraviolet or a visible ray. The scattered primary electron retains energy equals the difference of kinetic energy and binding energy. The relative contribution of characteristic X-rays to the total spectrum depends on X-ray target material, tube potential and filtration. Energy and intensity of K X-rays are much more than others. The L X-rays of tungsten, with energy below 12 keV of energy, cannot penetrate human body. Hence cannot reach detector to form image. Consequently, they are useless in diagnostic imaging. In fact, soft X-rays like L X-rays are totally absorbed by a typical filtration of 2.5 mm aluminium. For tungsten targets below 69.53 kV there is no K-shell characteristic X-rays. The fraction of K radiation contributing to the total energy fluence is less than 10% for a 100 kV tube voltage. Percentage of K characteristic X-rays first increases with kV up to 150 kV and then decreases with increase in tube potential. Hence mostly continuous Bremsstrahlung X-rays play major role in diagnostic imaging. Percentage of characteristic X-rays in total X-ray spectrum is more in targets made up of low atomic number. This is because of electrons are less tightly bound in low Z material and higher electron density.